Go through a quick recap of some basic differentiation tips and tricks, and also how we can apply differentiation without thinking back to first principles every time. So if you remember my previous video on first principles, we finished off that video by stating that if we had a function which was of the form x to the power of n, we could differentiate that function with respect to x, or we could rewrite it as dy by dx instead of that notation, is going to be, well, it's going to be reducing the power by 1 and multiplying by the power. So if we had a function, let's say, of x to the 5, my derivative of this function, well, it'd be 5 lots of x to the power of 4, because I multiply by 5 and reduce the power by 1. What happens if there's a constant before the x? Well, again, we'd do the same thing. We'd multiply by 4, so that would give us 8, and we'd reduce the power by 1. If the power is a fraction, we can still do the same thing, and the same rule applies. So if we have a function of x to the half, we should also know that this is root x. However, I can only do it of functions which are x to the power of some constant. So x to the power of a half is the same as root x, but we want it in this form. So the derivative of f of x, well, multiply by the power and reduce the power by 1. So a half goes to a negative a half. And lastly, when we have something, and this is a fraction with a term of x on the top and a term of x on the bottom, we can differentiate it like this, and you'll see that when you do a2. However, this is quite easy to think about as 1 power of x, so it's x to the half divided by x squared, which we know would be x to the minus 2. So therefore, altogether, this is x to the power of negative 3 halves. Now I can differentiate this with respect to x, and that would give me negative 3 over 2, x to the power of negative 5 over 2. So for the following questions, it's really important that we make sure that we have our equation of y equals or f of x equals or whatever in this form of x to the power of something. So I'd like you to pause the video and I'd like you to have a go at these questions, please. Okay, and I'm just going to go through the answers. So this first one, we should get dy by dx equals 7x to the 6. For the next one, dy by dx should equal 30x to the 9. For this one here, similar to what I did, exactly the same as what I did on the last slide, so we should have got this straight away. Except for one thing we should notice is because it's given as a function of x, we would have to write the derivative like this. And this would give us, well, what did I have on the last slide? It was minus 3 over 2 x to the power of minus 5 over 2. Negative. This one here, we're going to, well, multiply by a, so it's going to be a squared, lots of x to the power of a subtract 1. And lastly, 49x to the 7, I want to first of all rewrite this into a form which I can deal with. So by introducing that square root to the 49 would give me a 7, plus or minus, x to the power of 7 over 2. So now when I differentiate this, my f of x, well, 7 over 2 multiplied by 7 is going to give me 49 over 2. And x to the power of 7 over 2 subtract 1 is x to the power of 5 over 2. So well done if you had a go at those questions and you got most of them right. Please check any corrections before we move on. But as we move on, the next logical step to think about would be what would happen if I had multiple terms in a sequence. So here I've got y, and it could be some function, let's just call this f of x, g of x, I don't know, f, g, h of x. These are all functions, and if I want to differentiate y with respect to x, that's going to be the same as the derivative of f of x, add the derivative of g of x, add the derivative of h of x. So I can just differentiate each of these functions separately, each of these terms, sorry, and that would give me my derivative for y. So therefore, for this question, the derivative of y is going to give me, well, this would turn to 2x, this would turn to 4, and our constant term here, well, if we think about what we're finding, we're trying to find the gradient at a specific point. This graph of y equals x squared plus 4x would have the same gradient as the graph of y equals x squared plus 4x plus 3, because this plus 3 is just a translation vertically on the y-axis of 3 units. So therefore, this would be my gradient function, my derivative of y equals x squared plus 4x plus 3. So again, I'd like you to pause it and have a go at these questions. I've stipulated where the other variables are actually just constants. So have a go. And so for the first one, dy by dx, we should get as 4x subtract 3. For the next one, dy by dx, well, this 4 is a constant, so it reduces to 0. It has no bearing on the actual graph, so it's going to be equal to, well, negative 27x squared. For the next one, it's just a straight line. We should know the gradient is just the coefficient of x, and if we follow our same rule, we would also know it would be the coefficient of x as just 5. Likewise, for this one, it's just a straight line with the coefficient a as the gradient, so therefore our gradient must be a. But again, if we did the same rule, we would see that we are correct. And lastly, for question 5, dy by dx is going to be equal to 6. Then this subtract 3 goes to 0, plus px squared, so it's going to be plus 2px. So how does this look in terms of on an AS level paper? What types of questions are we going to see? Well, this is just a standard form that they would ask it in. So let f of x, so I'm just going to start off and rewrite this, equals 4x squared subtract 8x plus 3. And I want to find the gradient of f of x at this point. So as soon as I want to find the gradient, the first thing I'm going to do is I'm going to actually differentiate my function and get a gradient function. So my derivative is going to be equal to 8x subtract 8. And if I want to find the gradient at the point a half, I'm going to look at my derivative function where x is equal to a half. So it's 8 lots of a half subtract 8, which will be equal to negative 4. So at a half 0, the function of x is equal to negative 4. So that would be all I'd need for part A. Just going to make that a little bit smaller. Find the coordinates of a point of a graph of y equals f of x where the gradient is 8. Well, luckily, I've done some work here where I know that my gradient function is equal to, oh, that's an awful x, is equal to 8x subtract 8. And if I want to know when this is equal to 8, all I have to do is say that 8x subtract 8 is going to be equal to 8. So a little bit of rearrangement would give me 8x equals 16. Therefore, x must be equal to 2. So, at x equals 2, that is my x coordinate. It is asking me for the coordinates. So I want to know what y is equal to. To do that, I have to substitute it into my f of x function. So f of 2 is going to be equal to 4 lots of 2 squared, subtract 8 lots of 2 plus 3. Well, 4 times 4 is 16, subtract 16 plus 3, my answer will be equal to 3. So at x equals 2, y equals 3, and my gradient is equal to 8. Therefore, coords is 2, 3. Just something to just make sure you're explicitly answering the question that they are asking you. And finally, find the gradient of f of x where the curve, find the gradient of f of x at the points where the curve meets the line y equals 4x subtract 5. Okay. Now we have a classic example of where we have some sort of function. Let's say it looks like this, and we have a line, and we want to find the gradient at the point of intersection. So, first thing we'll do is find those points of intersections by setting these two equations equal to each other. So we've got 4x squared subtract 8x plus 3 is going to be equal to 4x subtract 5. By moving everything across, I get 4x squared subtract 12x plus 5, so plus 8 is equal to 0. I can divide through by 4 to get x squared subtract 3x plus 2 is equal to 0, and that will give me values of x plus x subtract 2, x subtract 1 equals 0, therefore x equals 2 or x equals 1. Luckily I know the gradient when x equals 2, because as x equals 2 my gradient is 8, so at x equals 2, f dash of x, so my gradient function is equal to 8, and I'm just going to move this up a little bit. Oh, I don't mean to do that. Just so I can write down underneath, at x equals 1, my gradient function is going to be equal to, well, let's think about it. 8 times 1 is 8, subtract 8 would be 0. So that's how it would look like on an exam. It's really beneficial to make sure that you can differentiate any sort of polynomial and any sort of x to any power really quickly and efficiently, because it is a very easy way to lose time in an exam if you need to resort to something like first principles to check your answers. If you have any questions on this, please let me know, and I hope you enjoyed. Thank you for watching.